Hello everyone. Today we are going to learn about three-phase AC system. Three-phase AC system. So generally we are going to represent this three-phase AC system or as three-phase terminals with red, yellow and blue. One terminal is R, one is yellow, one is B. So this is a nomenclature what we are going to use for use to represent three-phase system. Now, if you see this figure, this is the generation and whatever the power is generated that is given to the three-phase load. Three-phase load. So if you see the three-phase generator, here we are having three sources V1, V2 and V3. Three are single phase AC source only. This one is one single phase AC source and this one is one single phase AC source and this one is single phase AC source. That means here we are using three single phase AC systems. Then here the point we need to remember is how to represent three single phase AC systems to form or else to create three-phase system that we are going to learn now. And here by using three single phase systems we are having three terminals. We are having three terminals. That means this three-phase generator is having three terminals output. So from this one we are going to connect three-phase load only which are having three terminals, which are having three terminals 1, 2 and 3. So this is nothing but a load. This load can be a simple resistor or just a combination of reactive load. Okay, so R plus Jx, R plus or minus Jx, R plus or minus Jx we are going to say. Combinedly we are going to call this as impedance. Okay, so this one is a balanced load. This one is a balanced load. So balanced means these loads are having same amount of impedance. Okay, now we are going to learn to represent three-phase AC systems in clearly. Okay, so here the first one is balanced three-phase voltage. Balanced three-phase voltage. So as I have mentioned already, these three-phase voltages are created or made by three single-phase AC sources only. Three single-phase AC source only. Here I have shown you already. So these three single-phase AC sources. Let us say take one V is equals to Vm sine omega t. This is single phase AC voltage source expression, right? Now coming to three phase balanced voltage, that is three sinusoidal voltages of the same magnitude or same amplitude frequency but differing by 120 degrees phase difference, differing by 120 degrees phase difference with one another. That means, see here, the first voltage expression is V is equals to Vm sin omega t. The other two voltages, let us take V1 is equals to Vm sin omega t and V2 is equals to Vm sin of. So here amplitude and frequency both are same. What is the difference here? The phase angle is the difference. That is how much? 120 degrees. So sine of omega t minus 120 is for one expression. Let us write other one. So V3 is equals to Vm sine of omega t. So let us say this is 0 degrees. From 0 to 120 degrees displacement. From 120 to another 120 you are going to get 240 degrees. That means, so these are the three voltage sources, three single phase voltage sources which are having same magnitude and same frequency, and the thing is the phase difference. What is the amount of the phase difference? 120 degrees. The phase difference between any two phases, any two AC sources is 120 degrees. 120 degrees. Okay, so let us see by the representation of phasor angle as well as representation of these three waves now. Hope this one is clear. Shall we move to next slide? Now here, this is the representation of three-phase source. Three-phase source R load which are having a star connector load as well as a delta connector load. Star and delta. So star connected voltage source, delta connected voltage source. So star means three branches or three elements. One end is connected to the common terminal. Okay, so here this is one branch, this is one branch, this is one branch. On these three negative terminal is connected to one point, one common point, which creates the star formation, the star connection formation. Okay, so here you can also represent this one as like this also, like this also. There is no compulsory to represent the star connection like this only. Okay, you can also connect in this manner also. Now coming to delta, this is the delta which is having a similarity of a triangle. This triangle has three sides. These three sides can indicate the voltage source as well as it can be also a load. It can be also be a load. So these are the three single phase voltage sources. This is a representation. This is a representation of three phase voltage source. Now, now coming to three phase sinusoidal waveform. So as already we discussed about single phase AC sine wave is like this, which is having 25 degrees, 360 degrees of 360 degrees of one complete cycle. It can be voltage or current. One positive of cycle and negative of cycle. Right? So this is the expression V1 is equals to Vm sine of omega t. Okay, so now so let us take the first one. Red is the first one. Red. So this is starting at 0 degrees. So Vm sin omega t plus or minus 0 means the phase angle of this expression is 0 degrees. Let us assume that this voltage is the starting at 0 degrees and moving into the axis, and to create 360 degrees. That means this period is about 360 degrees. That means it completed one complete cycle. Now, so other expression is V2 is equals to Vm sine of omega t minus 120. That means the phase angle between these two voltages is 120 degrees. That means already the first expression is started at 0 degrees, and the other one is other phase is going to start at 120 degrees. 120 degrees. So from this point it is going to stop. From this point it is going to start. So let us take yellow here. So this yellow here we are going to have, you can see the yellow color here, that is going to represent with the purple here, this one, so which is going to make a complete cycle. Okay, so for better understanding purpose I am starting from 120 degrees. Okay, so this is the first half cycle. Before the first half cycle we are having negative half cycle also, so that is going to have extension of this waveform. Okay. So next expression is V3. V3 is equals to Vm sine of omega t minus 240 degrees. So minus 240 degrees means, so minus the second voltage source is started 120 degrees this point, and other voltage source is going to start at 240 degrees. That means this is the point where other voltage source is going to start. Okay, now here, so from this point the blue color wave is going to start, so it is also going to make 120 degrees. Let us complete the cycle left side as well as right side. So we are going to get the three-phase sinusoidal representation. So in this three-phase sinusoidal representation, here the magnitude is same in all the instances, and also the phase difference between two phases is 120 degrees. Between two phases is 120 degrees. That means here we are getting a balanced three-phase voltage source. So which is going to be represented with three-phase sinusoidal waveforms. So like this, we are going to represent three-phase sine waves. Okay. Next. So here let us write pi group by 60 divisions, and we are going to make the pen marking here. This is one phase, and other phase is going to start at 120 degrees. So I am going to take at this point and next waveform is going to start at 240 degrees. So it's going to be like this. For post of cycle, we are having new to of cycle. So you can also extend like this. So this may be, here you can take this one as approximate only, okay, not to be perfect from this representation of sine wave. You can make it as approximate. Okay, so these are three phases. How to draw these three sine waves? You can remember this. So next is phase sequence. Next is phase sequence. So in this phase sequence, there is two kind of phase sequences. One is clockwise direction, other one is anti-clockwise direction. Okay, clockwise means here let us say this is A phase, B phase and C phase in the clockwise. Now coming to here, A phase, this B phase and C phase, right? C phase here. Okay, so this is a one voltage source which is belong to the phase voltage. Here also this belongs to the phase voltage. Phase voltage means the voltage between phase and neutral is nothing but phase voltage. So this is the phase sequence which we are going to consider to represent three-phase AC system. And every phasor is having 120 degrees displacement. 120 degrees displacement in any phase sequence. Okay, and also magnitude same in all three phases. You need to remember. So you need to draw the same length of the every phasor should have same length. Every phasor should have same phase length. So this is a representation of phase sequence. Now we are going to represent the relationship between the phase voltage and line voltage. The here they have here you can also consider ABC sequence as well as RYB sequence. Okay. Now here, as we studied in vectors VAB is equals to VAN, or else you can take VA minus VB. If you take this concept into this phasor addition or phasor of subtraction, I am taking VAN minus VBN. VAN minus VBN. Now here, let's go for VAN. What is VAN? Phase voltage. Phase voltage. So phase voltage here you can consider one VAN is equals to Vm sin omega t. That means here phase angle is 0. This you can write Vm at an angle 0 degrees. Right? So next VBN is equals to Vm at an angle 120 degrees. Next is VCN is equals to Vm at an angle minus 240 degrees. Minus 240 degrees or plus 120 degrees. Either way you can consider. Now here this VAN minus VBN. This you can write VAN at an angle 0 and VAN at an angle minus 120. An angle minus 120. So if you solve this one, you are going to get. So how to solve means here, we know in mathematical expression R at an angle theta is equal to. This is a polar representation. This is the polar representation. Right? This is the polar. This is a polar representation. That is R at an angle theta. This you can write R into cos theta plus J sin theta. So write this expression to expand this statement to get this one. That means here this VAB is equals to root 3 times of VAN at an angle plus 30 So if you solve this for any line voltage, you are going to get root 3 times of VAN, root 3 times of VAN, root 3 times of VAN. And also the first phase is having plus 30 degrees, next is having 120 degrees displacement. 32 minus 90 is having 120 degrees displacement, minus 92 plus 150 is having 120 degrees displacement. 120 degrees displacement. Now this statement of expression we need to represent in the phasor representation. We need to represent in the phasor representation. Let us see how to draw this phasor diagram to represent the relationship between the line voltage and phase voltage. So here every phasor is having 120 degrees displacement. Now let us take this as VRN, and this one is VYN, and this one is VBN. Okay, these three are line phase voltages. Now, so I am taking. So here we have mentioned VAN, right? You can also take that one. So right. So instead of this RY, we can also consider A. This one is B here. This one is C here. This VAN. And say this is VAN. This one is VBN. This one is VCN. Okay. So here we know that VAN is equals to VAB is equals to VAN minus VBN. So VAN. So here VAN is already there, but we don't have minus VBN. This you can write VAN plus of minus VBN minus VBN. That means here minus VBN we should consider. So here already plus VBN is there, plus VBN is there. So how to get minus VBN? So in the 4 quadrant, you can take this one as analogous to that one, x and minus x, and this one is y and this one is minus y. This is positive x, this is negative x. So here this is positive means this is going to be negative 1. Correct or not? So here this one is Take the mirror image of VBN. Mirror image of VBN. Right. Now from this point, draw a parallel line to this one, to VAN. Draw a parallel line to VAN. Now in the same manner, draw the parallel line from this point to join these two lines. You get, you get, you get. So just get the resultant of this one, which is going to give you the combination of VAB. VAB. Right? Now in the same manner, go for other one VBN. VBN VBC is equals to VBN minus VCN. So here VBN is there, but we don't have minus VBN. So we can take mirror image of VCN will give you the minus VCN. So again same method to get the resultant. Draw parallel line. So from this point also, you can draw balance. Just it is. So you try to get exact phasor diagram by using graph sheet. So here you will get the resultant from this point. This will give you the VPC. Okay. Now in the same manner, VCA you can get VCN minus VAN. So again minus VN is the magnitude of VN phasor. You can consider the mirror image of VN will give you the minus VN. Again same method to get the resultant. Draw parallel lines here on both the sides. So we'll get one resultant. So it is like this. So this is the line voltage of VCA. Line voltage of VCA. So here whatever you got the line voltages VA, B, VB, C and VCA. These three line voltages are also having 120 degrees phase displacement. Then only whatever the phasor representation is there, that is going to be correct. Otherwise it is going to be wrong. So in this way you can conclude the three-phase AC system as well as with star connection with relationship of line voltage is equals to 3-way pH at an angle 30 degrees. So here the line voltage is a phase voltage. Here phase angle is 30 degrees. So let us go for this analysis here. The angle between, see the red phasors here, red color phasors, VAN and VBN. The angle between this one is 120 degrees. This is 120, right? So here VCN is doing bisection of this angle. So this is 60, this one is 60, and this portion is 60 degrees. Now this portion 60 means again this VBC is bisecting this one, means this one is 30, this one is 30. That means line phase voltage and line voltage is having 30 degrees difference. So this is going to be seen in the case of star connection load as well as delta connection load. In delta connection, for currents we are going to get the line currents is equal to root 3 times of high phase. We are going to get the relationship. So which are also having 30 degrees phase displacement. So in this way you can conclude the three-phase system for star connected load. Thank you.